So we now start the next section, subsequences. Now we have seen different types of sequences. Some of them are convergent, which have a unique limit point, which is the limit of the sequence, whereas some sequences are not convergent and they may or may not have limit points, and when they have limit points, they don't have unique limit points, they have multiple limit points. For example, we can consider this sequence. Of course, we are talking about sequences of real numbers. The terms of this sequence are these: 1.1, 0.1, 1.01, 0.01, 1.001, 0.001, and so on. So you can clearly see the pattern in which the terms are appearing. Now if you look closely, there are two kinds of terms in this sequence. Those terms that are greater than 1, and they are in fact decreasing. 1.1, 1.01, 1.001. The next such will be 1.0001. So the number of zeros after the decimal point is increasing, and as such the terms are decreasing and they are getting closer and closer to 1. So you can imagine that this entire sequence has 1 as a limit point. The other type of terms are these terms, which are less than 1, and they are progressing like this: 0.1, 0.01. So here also, after the decimal point, the number of zeros is increasing, and these are approaching 0, giving us the only other limit point 0 of this sequence. And it turns out that 0 is in fact the limit inferior of this sequence and 1 is the limit superior of this sequence. The sequence as a whole is not convergent simply because it has distinct limit points, two distinct limit points. We know that a convergent sequence has a unique limit point, which is its limit. Now, although the sequence itself is not convergent, but it seems like it consists of two convergent parts, which in fact are obtained by considering these terms separately, these two types of terms. For example, if you consider only those terms where the suffix is odd, if our original sequence is this, say it is starting with 1, then the odd suffixed terms are these: A1, A3, A5, etc. If we write only those terms, then we get this sequence. It is also going to be a sequence. The next one will be 1.0001, like that. And if you collect the even suffixed terms, the second term, fourth term, sixth term, etc., then we get this other part of the sequence. So the entire sequence consists of these two parts, and if you look at the parts themselves as sequences, they are in fact convergent. This the top one converges to 1 and the bottom one converges to 0. So these two convergent parts of the original sequence are giving us the limit points 0 and 1, but the sequence itself is not convergent. So this entire situation, to describe this situation and to take advantage of the presence of such parts which themselves are convergent sequences, we have this definition of a subsequence. And the definition has that name itself, subsequences. And the definition goes like this: let an and bn be sequences of real numbers. We say Pn is a subsequence of An if there exists a function, say f, mapping the set of natural numbers into itself, which is strictly increasing. That is, f of n plus 1 is greater than f of n for all natural numbers n, such that Pn is equal to a f of n for all n belonging to the set of natural numbers. Okay, so this is the definition of a subsequence. So that means what we are saying here, two sequences are given to us, An and Bn. We say that Bn is a subsequence of An if there exists a strictly increasing function on the set of natural numbers, also taking values on the set of natural numbers, such that any term Bn in this sequence is actually equal to some term An, and in fact the suffix is f of n. So the nth term in this sequence is the f of nth term in the original sequence. If this happens for all natural numbers n, then we say that Bn is a subsequence of An. So to better understand what is going on, let us take examples. So this is the first example. This one is of a slightly general nature. If An is a sequence of real numbers then a2n is a subsequence of an since the function f mapping the set of naturals into that set defined by this formula f of n equal to 2n is strictly increasing. And which we can clearly see, I mean, this notation itself tells us what the function f should be, and that this particular function turns out to be a strictly increasing function. Now there are some things to note here. Note that we do not assume f to be bijective. We are just requiring the function f to be strictly increasing, and that is not equivalent to being a bijection. We do not require f to be bijective, although f is necessarily injective. And this entire thing can be expressed more loosely or informally like this. A0, A2, A4, etc. This is a subsequence of our original sequence. Now what is happening? So we understand that this is a subsequence of this sequence according to the definition. But what is the definition saying actually? This is in fact more illuminating. This last line, A0, A2, A4, etc. These terms form a sequence which is a subsequence of the original sequence. Now if you look at these terms, what do you see? We see the fact that from the original sequence we have just chosen some terms, and we have formed another sequence out of those terms, and we are calling that new sequence a subsequence of the original sequence. Precisely for this particular example, we are choosing these terms, those terms where the suffix values are even natural numbers. So the function that we are seeing here, that function actually tells us which terms we should choose. This particular function tells us that we should choose the even suffixes. And okay, so we understand what the function f is doing. F in fact tells us exactly which terms we should choose. But what why do we need f to be strictly increasing? Where is that coming from? Note that all we are doing is in this task of choosing terms, we are actually concentrating on the suffix values themselves, 0, 2, 4, etc. So the original sequence along with it also brings a sequence of suffix values, which are of course nothing but the natural numbers. And what the function f is doing, f is helping us choose from those suffix values that will give us the terms of the subsequence. So f is telling us to choose 0, 2, 4, etc. You see that whatever you choose, ultimately you should have an object that itself is a sequence. That means what does that require? That requires that we choose infinitely many distinct values from these natural numbers using that function. The function should be such. Now, because the sequence of natural numbers itself is strictly increasing and we need to choose infinitely many values from it, so the function f that will help us in that choice, that should itself be increasing because its values should be those values. Okay, so that's why that's where the strictly increasing nature of f is coming from. This is one way of viewing this thing. Another way of viewing it is like this also, which you can say, if you want, a complementary way of describing the same thing. Instead of saying that we are choosing some terms, you can also view the process of getting a subsequence from a given sequence like this. You remove some terms. Whatever is left, that is a subsequence. The only thing is that you should make sure that whatever is left is a sequence. It should be a sequence. For example, from this original sequence, you can say that I am going to remove all the terms except a naught. Then you are left with a naught, which is not a sequence. So that type of removal is not allowed. After removing, if you still have a sequence, then that gives you a subsequence. Okay, so that's just it. You have the original sequence, you remove some terms or you choose some terms, whichever way it is convenient for you to understand. You can think in that manner. So you do that operation, whatever you have after performing the operation, that is a subsequence, and that in fact is the meaning of a subsequence, the definition of a subsequence. This function, existence of this function, you can now understand it comes necessarily. Okay. Now there are some other things that have been said here by the author. Note that we do not require f to be bijective. That is because we see that this particular f is not a bijection. It's not a one-to-one onto function because it's not onto. The images are all even natural numbers, so the odd natural numbers are being missed by f. However, that we don't need that. We only need f to be strictly increasing. Although f is necessarily injective, and this injective nature of f comes from f being strictly increasing. Two different inputs, say n and m, so these are two distinct natural numbers. They cannot give you the same f value. They will give you different f values. Why? That is because their not being equal implies either n is less than m or n is greater than m. Without loss of generality, you can assume that n is less than m. Then it's very easy to verify that f of n is also less than f of m. In fact, this is not immediately clear, although we can guess that this will happen, but it's not immediately clear just from the increasing nature of f. This has to be proved using induction, but this is a simple proof. Okay, so that is why, and this implies this, so this implies this. That means distinct inputs give us distinct outputs. So that's why f is injective. But f is not necessarily surjective and hence not necessarily bijective, like this example. Okay, so this is the idea of subsequences. Let us see another example. Now this example is the one with which we started. The two sequences and are both subsequences of that original sequence. In the beginning we saw it. And here, if you really want to be rigorous with the notations and everything, you can denote this sequence like an, where n varies from 0 to infinity. So a0 is 1.1, a1 is 0.1, and so on. Now, this first subsequence will be this. Consisting of the even suffixes, and this second subsequence will be this, consisting of the odd suffixes, and they follow the definition because the functions that we see here are f and g. F is this is an increasing function, g, this is also an increasing function from the set of natural numbers into itself. So that's why they are actually subsequences. And more loosely, and which is more illuminated, which is a better understandable way of going through, of getting this thing, is that this sequence is obtained, the first subsequence is obtained by removing some terms from the original sequence, and the first subsequence itself is a sequence, so that is why it's a subsequence. Just like that, if you remove these terms from the terms that are appearing in the first subsequence, if you remove them from the original sequence, then you are left with this. So this second one is also a subsequence. Now next we come to the first result of this section. If we think of the set of all sequences of real numbers, okay, that set can be considered. On that set, if you consider this relation of one sequence being a subsequence of another sequence, then this relation is symmetric and transitive. And the lemma specifically says this: let an Bn and Cn be sequences of real numbers, then An is a subsequence of itself, so that being subsequence is reflexive, and that other transitivity condition also can be similarly stated. Then An is a subsequence of An. Furthermore, if Bn is a subsequence of An, and Cn is a subsequence of Bn, then Cn will also be a subsequence of An. There are almost always two aspects of a mathematical concept or idea or whatever you want to call it. One of them is the absolutely rigorous concept where you use mathematics and its rigorous tools and techniques to define something, some concept. And because of that rigor, when you look at such thing, it looks quite abstract. For example, the definition of subsequence involves that increasing function and so on. If someone looks at it for the first time, it feels like an abstract thing, and this in general is true for anything in mathematics. From far away, the things look abstract because they involve those rigorous symbols and everything we have in mathematics. However, the other aspect is the intuitive aspect. If you understand the idea, if you understand what's going on behind those symbols, that is the real understanding. If you develop an intuition for the thing, then only you have understood it. Okay, if you just blindly follow whatever is written in the definition and then using those things in succession, you verify that an example, okay, so this is a subsequence because there is an increasing function, and that is why by definition it's a subsequence. Yes, that is true, but that understanding, that intuition in the background should be there. It's not easy to gain intuition about everything in mathematics. Some things are so the intuition follows only when you have understood all the things involved in that definition. You have really digested everything and you have connected all the parts of that, all the aspects of the thing in your mind, and then only you can gain that intuition. And once you have an intuition about some concept in mathematics, you will then see that many things you will feel should be true, and many things are it should be true about that mathematical concept, which later turn out to be true, because you feel that something should happen. In your mind you should be able to see the whole thing at once, maybe vaguely. Okay, so that intuitive idea should be there in your mind. From that you will see that, okay, it's like this, then this should be true. Such things will then flow from that intuition. The things will flow out, and then you can use mathematics to verify those things. That's how new things are found. Okay, so and Cn is a subsequence of Pn, then Cn is also a subsequence of An. Okay, I can now see I have forgotten something about, I should have told that thing. It's one aspect of the definition of subsequences. It's something very minor, but still it should be mentioned. We have been considering sequences where the index starts from 0. However, by now you know, we have seen many times that this actually does not matter. You can start from any integer. So if in the definition of subsequences you consider sequences where the indices start from some integer m, then that strictly increasing function no longer is a function from natural to the natural set. It will be a function from the set of integers starting from m to itself. Okay, so if you start like this, then you accordingly modify the definition. And in fact, there is no need to start from m in both the sequences. You can in fact start this from 0. In that case, your first set will be this, the second set will be the set of natural numbers. We will prove this, but in the exercises. Now here the next two propositions relate the concept of subsequences to the concepts of limits and limit points. Subsequences related to limits. Here the statement is this: let an be a sequence of real numbers and L be a real number. Then the following two statements are equivalent. Equivalent means each implies the other. Or the same thing, each follows from the other. Or I have to complete this sentence: each follows from the other, and the statements are these: the sequence an converges to L, that is, it has L as its limit, and the other statement is every subsequence of an converges to L. Its proof also is an exercise. It is the fourth exercise. And there is another proposition that relates subsequences to limit points. Proposition 666. Subsequences related to limit points. I like this number very much. 666. Here the starting is the same. Let an be a sequence of real numbers and let L be a real number. Then the following two statements are equivalent. A L is a limit point of our sequence and B there is a subsequence of the original sequence that converges to L. Okay, so that's how subsequences are related to limits and limit points. If a sequence is convergent, then its limit is also the limit of every subsequence. So that means every subsequence is convergent and has that as their limit, common limit. Conversely, if every subsequence of a given sequence converges to some common limit, then the sequence also converges to that limit. In this one, if a real number L is a limit point of a sequence, then the sequence has a subsequence that converges to L, and conversely, if the sequence has such a subsequence, then the limit of that subsequence is a limit point of the sequence. Its proof also is an exercise. There is, however, something we will prove in this video. So this is the fifth one. Before that thing, there is a remark. The above two propositions give a sharp contrast between the notion of a limit and that of a limit point. So when a sequence has a limit, when a sequence is convergent, then all of its subsequences all are also convergent and they have that same limit. If a sequence converges to a real number L, then all subsequences converge to L. Whereas when a sequence has a real number L as its limit point, then only some subsequences converge to L. Some subsequences means this proposition guarantees that there is at least one subsequence that converges to L. There may be more, but not necessarily all. Okay, so that is the difference. The difference is in all and some. We can now prove a result that is very important, an important theorem. In real analysis, due to Bolzano and Weierstrass. You may already know Bolzano-Weierstrass theorem about steps. There is one about sequences also. They are similar. Analysis due to Bernard Bolzano. Who lived in this time period and Karl Weierstrass. and this is the theorem: every bounded sequence has a convergent subsequence. So this is our next item. Okay, so the statement has been written in this way: let an be a sequence of real numbers that is bounded, or more directly, let an be a bounded sequence, let us mention, of real numbers, since we have been doing that everywhere. Real numbers, that is there exists a real number m which is positive, such that the absolute values of all the terms of the sequence are less than or equal to m. Then then there is at least one subsequence of an which converges. This one we are going to now prove. So we start the proof by considering the limit superior of the original sequence, which always exists. Let L be the limit superior of an, since now our next job is to show that L is actually finite, and in doing that we are going to use boundedness of our sequence. These inequalities, they are equivalent to this, since for all indices n it follows from the comparison principle, which is your lemma 6.4.13. that minus m is less than or equal to L and L is less than or equal to M. Let us briefly recall the comparison principle. In the comparison principle, we had this. Say AN and BN are two sequences, okay, such that AN is less than or equal to BN for all suffixes. Okay, we are not showing the variation of the suffixes because that does not matter. Then the limit superior of AN is less than or equal to the limit superior of BN. In fact, the comparison principle says other things, but we don't need those parts. We only need the limit superior part. Now here, in place of AN, we of course have our AN, and in place of BN, so let us see one of these two inequalities. The BN sequence is the constant sequence. All of those terms are equal to M. Now we have this and we have this. Now since a constant sequence is convergent to the limit that is equal to that constant term, so its limit superior is also equal to that is M, because we have seen in that we can call it the fundamental theorem of limit superior and limit inferior. There we have seen that for convergent sequences, their limits equal the limit superior as well as the limit inferior, and the converse is also true. In fact, we used the converse to prove that the system of real numbers is complete. So that part we are using. So this is equal to M, so that means what? L is less than or equal to M. Similarly, if you consider the constant sequence, all of whose terms are equal to minus M, you can then again apply the comparison principle, and you can get this inequality: minus M is less than or equal to L. So that's how we are getting them. Now note that because M is a real number, so L also has to be a real number. It is trapped in between these two real numbers. That means L can neither be plus infinity nor minus infinity. L is a real number. In particular, L is a real number. Without writing so much, we are just simply expressing it like this. Okay, so now L is a real number. Now note that L is a real number. The limit superior, when the limit superior is a real number, it is a limit point of the sequence. This also comes from that result on limit superior and limit inferior. The different parts that it has, one of them says this thing, that if the limit superior or the limit inferior or both, they are finite, then they are themselves limit points. So by now I will need the number. Part E of proposition 6 for 12. Which we write in short like this: proposition 6 for 12E. L is a limit point of our original sequence. So because L is a limit point of the original sequence, so by proposition 666, L is the limit of a subsequence. There is a subsequence of the original sequence that converges to L. And that's what we wanted to show. Now, there is a subsequence of an that is convergent. It converges to L fine, but we just need convergence. So here the proof ends. So that means in this proof we have used many things, but the things started with the limit superior of the sequence. We then showed using boundedness that is finite, and then finiteness of the limit superior implies it's the limit point, and then that proposition 666 implies there is a subsequence that converges to this. So looking at this whole thing, you can now see that instead of the limit superior we could have used the limit inferior also. We could have as well in the above arguments instead of the limit superior. Now there is this final remark 669. This remark I am going to write exactly how Tau has written: the Bolzano-Weierstrass theorem. Says that if a sequence is bounded, then eventually it has no choice but to converge in some places. It has no room. To spread out and stop itself from acquiring limit points. Yes. That I was rambling at one point about mathematical intuition. So this is the intuition behind this Poljanovic-Strauss theorem, that if the sequence is bounded, then it has infinitely many terms, not necessarily distinct. Okay, keep that in mind when we are thinking of sequences. Infinitely many distinct, infinitely many terms are there, but not necessarily distinct. But still, infinitely many terms are there. So if the area where you have the sequence is bounded, then it cannot it cannot spread out. The terms cannot spread out. There is no room for the sequence to spread its terms out, so that there is no chance of having any accumulation of the terms. There is no chance of having any limit point. That cannot happen because of the boundedness. So that is why it ends up acquiring some limit points, and that's how it has a convergent subsequence approaching those limit points as their limits or as its limit. It is not true for unbounded sequences. Bugs, for instance, has no limit point, and it also has no convergent subsequence. Now comes something that we will see later on. In the language of topology, this means that the interval consisting of the real numbers lying between -m and m, including the numbers themselves, that is, in other words, the closed interval -m, m, is compact, whereas an unbounded set is not compact. The distinction between compact sets and non-compact sets will be very important in later chapters. And in some sense, this is the situation is similar to, of similar importance similar importance to the distinction between finite sets and infinite sets. Okay, so this situation of being inside a bounded region and acquiring limit points is equivalent to, in the language of topology, the notion of compactness. And this is something that is very important in analysis. In fact, this Bolzano-Weierstrass theorem, that if you can trap a sequence of real numbers inside a bounded set, then there is a convergence of sequence. A part of the sequence has limit somewhere inside that set itself. This will be used in many places successfully to give us further insights into the situation. And this notion of topology, this arises, we will see these things when we go to the chapter that studies continuity of functions. Roughly speaking, if you consider an ordinary function, say this type of function, then you can draw its graph. Continuity means the graph is in one piece, it is not broken. And what that requires is that if you have 2 points in the domain that are close, in some sense very close, then they get mapped onto points, that is, if the inputs are close, the outputs should also be in some sense close. Because you see, if the inputs are close and the outputs are very far apart, the graph will break. You get discontinuity. From the surface of this whole thing, it may seem that this idea depends on distance between 2 points here as well as here, on the y-axis and on the x-axis. However, when one peers very deeply into the notion of continuity, one ultimately discovers that something else is there. I mean, something else entirely which at first glance seems like an abstract concept is at play. In fact, at the very base level, something else quite different from the notion of distance is at play, which is actually responsible for continuity and everything. When one investigates that notion, that setup, one discovers topology. Okay, we will see these things. So the section ends here, and in the next part, next Sunday, we are going to solve the exercises. And then once that is over, we will then have only one more section left in this chapter, which explores real exponentiation. So that's it for tonight in this video. If you want to say something, you can write in the comment section below. And so today is Sunday. On Tuesday, we again have graph theory. I don't know when this any of these things that we have been going through, they will be over, but when we near the completion of something, we will start something else. For example, ring theory is almost complete, and I have said that I am going to somehow summarize and complete it entirely. I mean, at least from Herstein's topics in algebra, we have to summarize everything that we have seen, and then naturally I should take up that commutative algebra, which I have decided to start from Atiyah and McDonald's book. So we will do that when we get time. When we see some time in between these things, we will do that. So that's just it. See you on Tuesday. Signing off from the mathematical room, sorry. This is me, Lucifer, and I am out.